Everyone. Okay, now what we realized from last time is that if we apply a torque, it is going to twist our shaft. And if one end is held constant, well, we can see that over time that angle of twist is going to increase. So let's consider this long, slender shaft of length L with a radius C that is fixed at one end. Now all the cross sections are subjected to the same internal torque T. The torque here is going to be the same as torque here, it's going to be the same as the torque here, all the way to the edge where it's finally canceled out by the wall. So in cases like this, the shaft is said to be in pure torsion. Now remember, a plane section before twisting remains plane after twisting. All those cross sections, they stay perpendicular to the axis, and all cross sections remain circular after twisting, and radial lines remain straight. And all the distance between the cross sections remain constant. All these things have to be true for what we're about to go into. We're in pure torsion, and all these things have to be true for what we're about to see. So it will no longer be the case, even if we're in pure torsion and we have a square section. So let's use what we know about how that torque twists the shaft to figure out the torsional shear strain. So what we're going to do is we're going to pull out one of those slices. When we were looking at it before, it might look like something like this. We got all these different slices. Well, we want to take one of those. That's what I just pulled out right now. So we've got some very, very small thickness, delta x. It's got an overall radius of c. And what we see is that over time, we rotate it because it's been twisted. And this line CD gets twisted down, and it's also angled. See, this is angled. Now, this right here, that's the strain symbol, the shear strain symbol. And it makes sense because what we talked about in the past was that the shear strain was when our cross section changed shape, or when we had these angles change. That's when shear strain came into it. Similarly here, the angle changed, and shear strain is the cause of that, or at least is the effect of that. Now, it might be fairly obvious here that if you look at it, the angle of twist and that shear strain, they look like they're going to be connected. Are they connected? Well, that's something for us to find out, but they look like they're going to be connected. The second thing to think about is that this line CD and CD prime, this is not on the outside surface. This is actually on the inner surface right here, which is a distance rho from my center line. So let's zoom in a bit. So first thing we can do is define shear strain as the distance between D prime and D double prime, right here, delta x. Now that's simply opposite over adjacent. Now if you're like, well, that's not quite the case because, that's a curved one right here. Remember that this is for very, very, very small angles, and so that curved line becomes a straight line when we go very, very small. At least it's similar enough to it that it doesn't matter. Now we can then generalize this by using our equation of twist, because what is the length of this D prime, D double prime side? Well, it would be simply the radius times how much I've twisted. In radians, always in radians. Okay? I might ask you at the end what's the angle of twist in degrees, but if you're using it in an equation, it's got to be radians. Never ever degrees. Now, what you see here is we have an angle of twist that's changing over a particular distance. This should hopefully look a lot like a derivative. And if you're wondering, oh no, there's going to be integrals and derivatives, yes, there will be. So be prepared for those. Now, using that equation, we can determine where the shear strain is at a maximum. And since it's proportional to this radius, well, it's pretty obvious that it's going to be at a maximum at the outer surface. And if we know what the max shear strain is, we can then rewrite our initial equation as a fraction of the max shear strain. As you can see, when the radius is 0 right here at the center line, the strain goes to 0. There is no strain, at least shear strain, at the center line. Okay, so we'll stop there for today, and I'll see you all next time as we start talking about torsional shear stress. So thank you for listening. I'll see y'all later. Bye-bye.